Welcome back. In this video, we're going to take a little digression and talk about formal languages. Formal languages play a big role in theoretical computer science, but they're also very important in compilers because inside of a compiler, we typically have several different formal languages that we're manipulating. Regular expressions are one example of a formal language, but it's actually helpful, I think, in understanding regular languages and all the formal languages we'll see later on in later videos to talk about what a formal language is in general. So let's begin with a definition. A formal language has an alphabet, so some set of letters sigma, and then a language over that alphabet is just a set of strings of the characters drawn from the alphabet. So in the case of regular languages, we had certain ways of building up sets of strings of characters, but other kinds of languages would have different sets of strings. And in general, a formal language is just any set of strings over some alphabet. An example of a language that you're familiar with is formed from the alphabet of English characters, and it is just the set of English sentences. Now, this is not quite a formal language in that we might disagree on which strings of English characters are in fact valid English sentences, but one could imagine that we could define some rules that would say that certain strings are English sentences and others aren't, and if we could come to some agreement, this would be a fully formal language. Now, a much more rigorous formal language would be something like the following. We could pick our alphabet to be the ASCII character set, and the language to be the set of all valid C programs. And this is definitely a very well-defined language. This is exactly the set of inputs that C compilers will accept. And the important contrast I want to draw here is that the alphabet is actually interesting. So different formal languages have very, very different alphabets, and we can't really talk about what the formal language is or what set of strings we're interested in unless we first define that alphabet. Another important concept for many formal languages is a meaning function. Typically, we have one of the strings in our language, and let's call that some expression E. And the expression E by itself is just a piece of syntax. It's a program in some sense, or it represents something else that which is the thing we're actually interested in. And so we have a function L that maps the strings in the language to their meanings. And so, for example, in the case of the regular expressions, this would be a regular expression, and that would be mapped to a set of strings, the regular language that regular expression denotes. And we saw an example where we wrote out the meaning function for regular expressions last time. So let's use regular expressions as an example, and I'm going to first write down the meaning of the regular expressions the way I wrote it down in the last video. So if you recall, we had a regular expression epsilon, and that denoted a set which contained just one string, namely the empty string. And then we had a regular expression C for every character in the alphabet, which also denoted a set containing just one string, namely the single character C. And then we had a bunch of compound expressions. So for example, A plus B, that was equal to the union of the sets A and B. And we had the concatenation, so I could juxtapose A and B, and that was equal to a cross product, where I selected a string from each set in order and concatenated them together. And finally, there was iteration. So I could write A star, and that was the union over I greater than 0 of all the sets A to the I. All right, and the interesting thing about this definition is you can see that we're mapping, over here we have expressions. Okay, let me switch colors here. Over here we have the expressions, and over here we have the sets. But there's something kind of odd about the way this is written, and not quite right, because you can see here where clearly we have an expression, we have a piece of syntax, A plus B, and then somehow on the other side, this A and this B have magically turned into sets that we're taking the union of. And similarly down here, we're choosing an element from this set, but this set is also an expression. And what does it mean? Somehow we're conflating the sets and the expressions. And this is what the meaning function is intended to fix, and this is what or intended to make clear. So what we really want to say is that there's some mapping that the language L of epsilon is this set. So L maps from expressions into sets of strings. Okay, it's a function that maps one to the other. And if you haven't seen this notation before, this is a standard notation for describing functions. It just says that L is a function from things in the domain, in this domain, to this range. Okay? And similarly, the language of this expression is this set. And it becomes really useful for the compound expressions, because here we say the language of this expression is equal to the language of A union with the language of B. And now you can see the recursion. First, we interpret A and B using L, and we take the union of the result. Okay, so now it's clear what's a set and what's an expression. And similarly here, the language of A concatenated with B, we are going to select elements from the language of these two expressions, and then we're going to form another set from those two sets. And finally, for iteration, the language of A star is equal to the union over the meaning of a bunch of expressions. A to the I is an expression. This is a piece of syntax, and we have to convert it to a set in order to take the union. And so now this is the proper definition of the meaning of regular expressions, where we've made the meaning function L explicit, and we've shown exactly how recursively we apply L to decompose the compound expressions into simpler expressions that we compute the meaning of and then compute the sets from those separate smaller sets. So there are several reasons for using a meaning function. We just saw one of them, which is to make clear what is syntax and what is semantics in our definitions. Some parts of the definition are expressions, and some parts are the meanings or the sets. And using L makes it clear that the arguments to L are the programs or the expressions, and the results are the sets. The outputs are the sets. But there are a couple other reasons for separating syntax and semantics. One is that it allows us to consider notation as a separate issue. That is, if we have syntax and semantics being different, then we can vary the syntax while we keep the semantics the same. And we might discover that some kinds of syntax are better than others for the problems that we're interested in or for the languages that we're interested in. And another reason for separating the two is that because expressions and meanings, because syntax and semantics, are not in one-to-one correspondence. And I actually illustrated this with regular expressions in a previous video. But I want to reiterate here that there are generally many more expressions than there are meanings. So that means there may be multiple ways to write an expression that means the same thing. I'd like to take a moment to illustrate why separating syntax from semantics is beneficial for notation. So everybody's familiar with our number system. So I can write numbers like 0, 1, 42, and 107. And there are very nice algorithms for describing how you add and subtract and multiply such numbers. But there are older systems of notation for numbers, things like the Roman numerals. So I could have the number 1, I could have the number 4, the number 10, and say the number 40, I think is written like that. And an issue with this number system, well, first of all, let me stress that these two have the same meaning. So the meanings of expressions in this language are the integers, and it's exactly the same in this language. So the idea, the meaning of these two systems are just the numbers. But the notation is extremely different. A number written in Roman numerals looks completely different from a number written in Arabic numerals. And the fact is that the Roman numerals are really painful to do addition and subtraction and multiplication in. And in fact, back in ancient times when this was a common system, it was not very well known how to do it, and very few people were actually good at doing arithmetic with this system because the algorithms were kind of complicated. And when we moved to the Arabic system later, it was a big improvement because it was easier for people to learn how to do basic arithmetic with these kinds of numbers. And the only thing that changed between one system and the other was the system of notation. And so notation is extremely important because it governs how you think and it governs the kinds of things you can say and the sorts of procedures that you will use. So don't underestimate the importance of notation. And this is one reason for separating syntax from semantics, because we can leave the idea of what we're trying to do, the numbers, alone and play with different ways of representing them. And we might discover that some ways are better than others. The third reason I gave for separating syntax and semantics is that in many interesting languages, multiple expressions, multiple pieces of syntax will have the same semantics. Going back again to regular expressions, let's consider the regular expression 0 star. Now, there are many ways to write this same language, which is the language of all strings of zeros, so strings of zeros of any length. So for example, I could also write that as 0 plus 0 star. Another way to write it is as epsilon plus 0, 0 star. And here you can see that this expression is all the strings of zeros of at least length 1, and then we get the empty string from epsilon. So this is equal to 0 star. And there's just, any combination of these things would also amount to an equivalent language, for example, that one, and so on. So there's actually an unbounded, unlimited number of ways I could write this language, but all of these mean exactly the same thing. And if you think about it, what this means is that in general, if I draw the two domains differently and I think about different expressions over here and different distinct meanings over here, and the function L that maps between them, the function L is many to one. So there are, there are points in this space that where many different expressions or pieces of syntax map to the same meaning. And this is just a general characteristic of interesting formal languages. And this is actually extremely important in compilers because this is the basis of optimization. The fact that there are many different programs that are actually functionally equivalent, that's what allows us to substitute one program that runs faster than another. That's what allows us to replace one program with another if it runs faster and does exactly the same thing. So we couldn't do optimization. The reason we can do optimization is precisely because the meaning function is many to one. So meaning is many to one, and keep in mind, important point here is that it's never one to many. We don't want the opposite situation. If we had the opposite situation where L could map a single point to two different meanings, well, first of all, this would no longer be a function, but also it would mean that the meaning of certain expressions, say in our programming language, was not well defined. That when you wrote a program, it was actually ambiguous whether it meant this or it meant that, and that's a situation we don't like. So we expect our meaning functions to be many to one for non-trivial languages, and we don't want them ever to be one to many. And that concludes today's video. Next time, we're going to go back and continue with our discussion of lexical analysis.